Now that we've sort of looked at how we can use the zeros of a polynomial to graph them, right? We've kind of started our study of graphing these polynomials. The next thing we're going to look at, sort of the next couple of lectures, are going to flesh out this theory of the zeros of the polynomials and more explicitly, how to find them. And the first way that we're going to do that is we're going to look at what is everyone's favorite, or rather more often least favorite, thing that we learn in grade school and then comes back when we do polynomials, and that's long division. But I want to kind of motivate the weirdness of the way that we tend to write things like that, right? And that's going to kind of go back and look at some of our definitions when we're talking about like regular division, right? Division of numbers, right? If we were to say, consider the fraction 38 over 7. Well, 38 over 7, that comes out, that's the same thing as 5 plus 3 over 7, right? There are, 5 times 7 is 35, plus 3 over 7 is 38 over 7. And this is the way that we normally think about it, right? And we can sort of label these component parts, right? We have 38 as our dividend, we have 7 as our divisor, 5 is known as the quotient, and 3 over 7 is our remainder, okay? Suppose I'll move this down just so we have a bit more room. But so this is the normal way that things are written out. Another way that you'll see not particularly often with numbers, but we'll see a lot with our polynomials, okay, is this form right here, where remember that this guy just basically tells us that we can go both directions, right? One implies the other, and that's 38 is equal to 5 times 7 plus 3, right? This is the way that some of you might think about doing this problem, right? That for 38, we have 5 sevens and then a 3 left over. And this is the way that more often than not we'll actually think about polynomial division. Not all the times, but just sometimes, okay? But this idea gives rise to something that we call the division algorithm, okay? So let me define that for you. This division algorithm can be implemented lots of places. You see it in number theory, you see it in lots of other areas of abstract math, but it turns out to be very useful in polynomials, right? So here's our division album sort of for polynomials. So if p of x and d of x are polynomials with d of x not equal to 0, right? So that's a comma. Then there are two unique, that's really important, two unique polynomials, q of x and r of x, where r of x is either 0 or of degree less than that of d of x, such that, okay? And then here's where we sort of translate the previous thing, right? If we write p of x and divide that by d of x, well, that's equal to q of x plus r of x over d of x, right? And just as we can rewrite this statement, so too can we rewrite this statement in our sort of alternate notation, right? That's that p of x is equal to q of x d of x. Make that clear, that's a d, plus r of x, okay? Just as before, you might want to label this here, right? P of x is our dividend, d of x is our divisor, q of x is our quotient, and r of x is our remainder, right? And again, I want to sort of draw your attention to A, that these are unique, right? So given any p of x and any d of x, or any pair like that, right? There's always only one pair q of x and r of x, such that we can write them like this, okay? One thing that I want you to think about, right, is this statement right here, where r of x is either 0 or of degree less than p of x, okay? And I want you to think about why that might be necessary, right? What about this definition or construction falls apart if r of x does not have that property? Okay, let's do an example of this long division. Okay, let's say divide 6x squared minus 26x plus 12 by x minus 4. Okay, so we're gonna put one polynomial there, put our other polynomial here, 6x squared minus 26x plus 12, okay? And we want to, just like we did with long division back in grade school, we want to fill in things out here, multiply them by this, fill this in out, and all of that, okay? So the first question is, what do we need to multiply by x in order to get 6x squared, right? Well, it would seem to me like you should multiply that by 6x, because that is the missing factor, right? So now 6x times x minus 4 is 6x squared minus 24x, okay? And then we're going to subtract these, right? So 6x squared minus 6x squared is, wouldn't you see that, 0. Perfect, exactly what we want. And then minus 26x minus a negative 24x is negative 26x plus 24x, or minus 2x. And we drop down our plus 12. Okay, so now the question is, what do we need to multiply by x minus 4 to have my leading term be minus 2x? Well, that would look to me like minus 2. So this is going to come out to minus 2x, looks like plus 8. Once again, we're going to subtract these, right? Negative 2 plus 2x is 0. And 12 minus 8 is 4. I guess I'll write those back in the correct color for the sake of color coding. Okay. This 4 right here, this is my remainder. Okay. Which means we can, so let's sort of write this the two separate ways, right? First way, so 6x squared minus 26x plus 12 divided by x minus 4 is 6 minus x, or is 6x minus 2 plus 4 over x minus 4. Okay, so when you divide this by this is the expression we get. Okay, this is our, quotient and our remainder. But as I said before, we can write this in an alternate form, right? Many of the questions will say, find q of x and r of x such that the division algorithm holds or whatever. So that way would be 6x squared minus 26x plus 12 is equal to 6x minus 2 times x minus 4 plus 4. Okay, let's do another one. Let's say, for example, we'll let p of x equal 8x to the fourth plus 6x squared minus 3x plus 1, and we'll say d of x is 2x squared minus x plus 2, right? And just as I said before, we're going to find q of x and r of x, not p of x, such that the division algorithm holds q of x times d of x plus r of x. Okay. So let's do this with our classic long division. We write our p of x in here. One thing that we want to do during this process is all the terms that might have a 0 coefficient, we still want to write them. Okay. And then we're dividing this guy by 2x squared minus x plus 2. Okay, so the first question, as I said before, is what do we need to multiply this by in order to cancel this 8x to the fourth? Well, it would look to me like the thing we're looking for is a 4x squared. Right, so 4x squared times 2x squared minus x plus 2 is going to be 8x to the fourth. That's going to be minus 4x cubed plus 8x squared. Perfect. Now we're going to subtract these two. 8x to the fourth minus 8x to the fourth is 0. 0x to the third plus 4x cubed is going to be 4x cubed. And 6x squared plus 8x squared is going to come out to minus 2x squared. Now let's drop down this 3x and keep going. What should I multiply this guy by in order to get a 4x cubed? Well, it would look to me like we would want a 2x there, okay? When I multiply this out, 2x times 2x squared is going to be 4x cubed. 2x times minus x is going to be minus 2x squared. And 2x times 2 is going to be 4x. Now we subtract these. 4x cubed minus 4x cubed is 0. 2x squared, negative 2x squared plus 2x squared is 0. Okay. But then 3x minus 4x is going to be negative 7x. Drop down my plus 1. So now the question is, right, what in the world could I multiply this guy by in order to get negative 7x plus 1? And the answer is quite simply nothing, right? This is our remainder. There's nothing that we can multiply this by in order to keep going. And that's because, notice that negative 7x plus 1 is degree 1, right? This is degree 2. There's nothing I can multiply to lower the degree, right? So we're done. We can write this in the form of this guy, right? We can say that p of x, or rather we'll write out p of x. We can say that 8x to the fourth plus 6x squared minus 3x plus 1. Well, we can say that that is equal to my quotient, q, which is 4x squared plus 2x, times our divisor, which is 2x squared minus x plus 2, plus our remainder, right? And I guess we'll label these for completeness sake. This is the q of x we had to find, and this is the r of x that we had to find. Now this idea goes a little slowly, right? We don't really like the way that it goes. Like it's slow, it's cumbersome, it's just not ideal. So we're going to introduce an idea called synthetic division, okay? And synthetic division will serve us very well as we seek to understand polynomials, better than one would think, okay? So let's say we're going to divide 2x cubed minus 7x squared plus 5 by x minus 3. And what's really, really important about the synthetic division process is it only works in situations where you're dealing with the division of some polynomial by a linear term. Any other situation, it's not going to work, but we actually end up dividing things by linear terms a lot. Okay, actually, further, more specifically, it only works with linear terms with 1 as my coefficient for x. Now that may seem a little bit restrictive, and it is. There's lots of division that we may want to do that's not this, but it actually turns out that it's very, very useful, right? It comes up all the time. So I'm going to first walk you through the way that you would divide this using traditional division, right? X minus 3 into 2x cubed minus 7x squared plus 0x plus 5. First thing we're going to want is the 2x squared, right? It's going to give me 2x cubed minus 6x squared. We're going to subtract these. That's going to leave me with a 0 and a minus x squared, right? Drop down my 0x. And then what happens next, right? We're going to have a minus x to get a minus x squared plus 3x. We're going to subtract these, okay? And that's going to give us 0 and minus 3x. Then it looks like the last thing we're going to have is a minus 3. Need to drop down that plus 5. And that is going to come out to minus 3x plus 9. Or when we subtract these, a remainder of 4. Okay. Not too bad, right? It's possible. It's not necessarily crazy difficult. It is a little tedious. But let me show you a faster way to do this. So when we do synthetic division, we write this guy in the corner, right? When we have x minus, some number h, we write the h right there. And then it's traditional to draw this thing that looks like an L kind of on its side. And then we fill in here the coefficients of our polynomial in order, okay? Where we remember to add zeros for all of our zero coefficients. And we draw another line down here, or at least I like to draw that line. And let me walk you through the process, okay? We're going to drop this 2 straight down, and we're going to write a 2, okay? That 2 corresponds to this 2 right here. We now multiply this 2 times 3 to get 6. That 6 corresponds to this 6 right here. Then we add vertically like this, right? That corresponds to this vertical addition here. When we add vertically here, it looks like we're going to get -1, that -1 right there. Multiply once again that by 3, and we get -3. Notice that this -3 looks like this -3, right? Where just as up here, right, that it does have a positive sign here, but this subtraction flips our sign. It's just a little thing to note. Add straight down, we get -3. That corresponds to this -3 right here. And then we multiply again. 3 times -3 is -9. much like this negative 9. And adding straight down, looks like we're going to get negative 4. This negative 4 right here that I didn't catch, that should be negative. So just by taking our thing and instead of doing all this, right, we drop down, multiply, add, multiply, add, multiply, add. If we remember what our coefficients are, well, this guy is my quotient, right? Just like this is my quotient. And this is my remainder. Just like this is my remainder here. Okay. That's the power of synthetic division, right? And we will do a lot more examples of this. I want to draw your attention to one really, really important theorem that will sort of kind of draw this home of like, why do we care about this, right? Why is synthetic division useful? Okay. And that's this theorem right here. It's called the remainder theorem. Okay. And it goes a little something like this. If you divide a polynomial let's give our polynomial a name, say p of x, by x minus c. Well, then the remainder is the value of p of c. Okay, so when you divide your polynomial by one of these linear terms that looks like x minus c, the remainder is the polynomial evaluated at that point. Okay, we can sort of do a little 1 or 2 line proof of this, right? Let's say we divide it by x minus c. We're going to get some q of x plus our remainder. And note that this remainder must either be 0 or some number, right? There's no other option because it needs to have a degree less than this guy, which is 1. But then what's p of c? Well, p of c is c minus c times q of c plus my remainder, but c minus c, that's 0. So the only thing left over is my remainder. So if we're looking for places where the polynomial is 0, if we divide by this guy and we get 0, awesome. If we divide by this guy and we don't get 0, we still get a point on our graph, right? We'll do one example of using the remainder theorem, and then we'll look at another theorem and do some examples with that, and then we'll wrap up for the day. So let's say, or rather, so let's find the quotient and remainder. Remainder, that's spelled close enough. When dividing p of x equals 3x to the 5th, say plus 5x to the 4th, minus 4x cubed, plus 7x plus 3. Big long polynomial, we're going to divide that by x plus 2, and then use this to calculate p of negative 2. So let's jot down our synthetic division. We have negative 2 on the outside, then on the inside 3x to the 5ths, 5x to the 4ths, negative 4x cubes, 0x squareds, 7x's, and 3 is our constant term. Draw this line, and we'll draw this one as well. So the first thing we do is we drop this 3 down. 3 times negative 2 is negative 6. 5 plus negative 6 Looks like that to me is going to be -1. -2 times -1 is 2. -4 plus 2 is -2. Multiply to get 4. Add. Multiply to get -8. Add straight down for -1. Multiply -1 by -2 to get 2. Add straight down to get 5. Okay, so this is 1 degree less, right? Remember, this is going to be my quotient, and this is going to be my remainder. This is a 5th degree polynomial, so that means this is going to be a 4th degree polynomial. So that means we're going to have p of x. We'll write this guy first. Looks like we're going to have 3x to the fourths, -1x cubes, -2x squareds, 4 x's, and a -1, and then a lowly 5 is right there at the end. But as we just saw, we can read off right away that p of -2 equals 5, right? Either by just looking here, or again noticing that -2 makes this term 0. 0 times anything, well, is also 0, so that thing goes away and we're left with just 5. As I said, I have another theorem for you. This is going to be the factor theorem. Okay. And we used this a little bit earlier, but we are actually going to prove it, right? And the factor theorem says that C is a 0 of P if and only if x minus C is a factor of P, okay? And we're not just going to take my word for it like we do often for these theorems. Once again, this proof is a little short, so we're going to go ahead and do it. Since this is an if and only if, we need to show that the statement holds going this way and going this way. Let's go say the forward direction first, right? So let's say C is a 0 of P, right? So P of C equals 0. Well, then by the remainder theorem that we saw just before, P of x is x minus C times Q of x plus 0, right? For some Q of x. So P of x is x minus C times Q of x. But that's exactly what it means for x minus C to be a factor, right? It factors out of the polynomial. Okay, so let's go the other way really quickly. So say x minus C is a factor. So P of x equals x minus C times Q of x. Then, and I just realized that this guy is a line below where he should. Well, then P of C equals C minus C times Q of C, which equals 0, times Q of C, which is 0. Well, then x equals C is a 0 of P. Awesome, right? We sort of broke this down going both ways. Now, let's use this, right? So let's go and have some examples, okay? Let's say P of x is x cubed minus 7x plus 6. And we want to show that P of 1 equals 0. And then factor P completely. Okay. So here's what we can do, right? We can use synthetic division, right? As we just proved using the factor theorem, we can use synthetic division to find our factors. Setting this up, we have a 1 on the outside, and then it looks like our coefficients are 1, 0, -7, and 6. Dropping down my 1, I have 1. 1 times 1 is 1. 1 plus 0 is 1. 1 times 1 is 1. Adding straight down, we have -6. But 1 times -6, well, that's -6. Plus 6 is 0, right? So by our remainder theorem, we have that p of 1 equals 0. And because of how synthetic division works, we have that p of x is x minus 1 times x squared plus x minus 6. So now we've turned factoring a cubic function into simply factoring a quadratic. Well, how does that factor? Our x minus 1 stays. We're looking for two numbers that multiply to -6 and add to 1. I guess x plus 3 and x minus 2. Okay, so we've factored p completely. We'll do one more example. These ones are a little bit tricky. So let's say a polynomial p of x, let's say it's of degree 4. With zeros, -3, 0, 1, and 5. And the coefficient of the x cubed term is -6. And we want to find p of x. Okay, so here's what we're going to do, right? This may seem rather difficult or even impossible. We can sort of run through the math, okay? We know that each of these zeros corresponds to factors of my polynomial, okay? So that means the factors of the polynomial are going to be x minus 0, x minus a -3, x minus 1, and x minus 5, okay? And now we want to start to simplify this, right? This turns into x times x plus 3 times x minus 1 times x minus 5, okay? In the interest of time, I'm going to tell you that this comes out to x to the 4th minus 3x cubed minus 13x squared plus 15x, okay? Definitely go and verify that yourself, but again, in the interest of time, I'll do that multiplication for you. But we have a problem, and that is simply that our coefficient of x cubed is -3, should be -6. Well, there's one thing that this didn't account for, right? Our zeros give us the factoring, but who's to say that there isn't some scalar, a out here, right? So what would we want that scalar to be, right? Well, it would be really nice if we could multiply this whole thing by a +2, right? Because that way, when we distribute that +2 in, we get 2 times -3 getting -6. Okay, well, we would need that 2 there, and we would need that 2 there. And as I just sort of said, this representation of a polynomial, it's different than the original polynomial we wrote down, sure, but it's still a degree 4 polynomial with these zeros, right? So it's perfectly valid. So when we distribute it, we get 2x to the 4th minus 6x squared, sorry, that should be x cubed, minus 26x squared plus 30x, okay? By construction, right, this is degree 4 and has these zeros, and has the needed coefficient on x cubed. So I'm confident in calling that p of x, with that being our final answer.